Hi folks, we are back and we are at section 2.38 talking about periodic variables. So these are variables that will come up they'll come up quite frequently depending on the types of data that you're working with. So for example, this would be, for example, gives an example of wind direction at a particular geographical location. So, you want to put that on 0 to 360 degrees. Another one might be calendar time, or time over 24 hours, or over annual cycles. You want to see at what part of the day, for example, are people most active, or how does their activity vary with time in the day. And so those types of variables, they have this kind of cyclical property, and then we need to kind of treat them differently. So that's kind of what this section is about. I thought it would also be fun to just give you another example of this from kind of the sort of stuff that I work on. So let me switch over here. Okay, so this is from a paper. I didn't work on this paper, but it's from a lab that I did my PhD in. And what they were studying in this case was looking at the activity of the brain cells in the brain of a grasshopper when they expose the grasshoppers to different types of odors. And what I want you to focus on here is this particular plot. I think you can see my mouse. So the cool thing about it is that what you find is that when the grasshopper is responding to odors, its brain generates these oscillations, which you can kind of see in this kind of these wiggly lines. And then different brain cells will respond at different positions within that, different phases of that oscillation. And so you might, and the authors here were interested in exactly what that phase was, whether it depended on the odor or not. And so if we actually zoom down, then they did one of the approaches that we're going to touch on here, which is a simplest thing you might want to do is you might just build a histogram, and you'll say, well, these cells here, these KCs that I'm interested in, what phase of the oscillation do they tend to fire on? And you can see, okay, they tend to fire most of their activity. You've built this circular histogram, and you can say that most of their activity tends to come in this location, and it turns out regardless of what the odor is. And some of the cells that are upstream, they'll tend to fire kind of earlier in the oscillation. So these cells you're interested in are firing here. These other guys are firing a little bit earlier in the oscillation. So you want to be able to kind of work with these kind of cyclical variables, and then maybe be able to do kind of inference and say what the mean of that position is, of that that phase of the response is, and things like that. And for situations like those, you need to work with periodic variables. So that's what we're going to be talking about today. So let me switch back here to the normal position. Okay, so now the section actually it's a little bit long, but actually it's the ideas are quite simple. So, but I thought it would be useful to first kind of outline what kind of what we're going to be discussing. So the way it's going to work is first, and I think it's really great that he points out, so there's an example. There's going to be an example of periodic data, and kind of a problem that will arise if you treat it without acknowledging the periodicity. And the problem of ignoring periodicity. So ignoring the fact that, if you have an angle that's 1 degree, that's quite close to an angle that's 359 degrees, even though the numbers seem quite different. So then we'll kind of look at the solution, which is to, solution, place data on the unit circle. So effectively what this is kind of saying that, look, the nature of your data is different. It kind of wraps around. And so we're going to need to find the representation of that data that also wraps around, except, unlike the normal representation we use, which is kind of for real value data, which doesn't wrap around, which kind of just goes all the way out to infinity in both directions. So we're going to look at a kind of a simple, a solution of one aspect. So we're going to place data on the unit circle and find how that solves part of the problem. And then we'll look at, okay, so now what's the probability distribution we can work with? And it'll turn out that that'll be something called the von Mises distribution. And he will derive it in a particular way. And I'll kind of give you a guide of kind of what he's doing there, because I think he kind of does it. I think he could have explained it a little bit better. So hopefully I can kind of provide that background explanation for you. It's just a couple of lines, and then you'll And then the rest of it is just, we're just going to be doing the usual thing, which is just, doing, finding the distribution, the unnormalized distribution, and looking at it, and then doing the maximum likelihood estimates of its parameters, just the usual stuff, taking derivatives, setting those to 0. And you'll see it'll kind of give some nice solutions to the problem that we have. And then finally, he'll touch on, a couple of other alternative ways of addressing this problem. And I think one of them, which is called kind of wrapping, I'll actually talk about in the next video, because I think he doesn't go into it any further, but I thought it's pretty neat, so I'll talk about that in the next video. But as far as this section is concerned, it's just going to be the example of periodic data and the problem of ignoring periodicity, so that's what we're going to start with. And then we're going to place the data on the unit circle. That's going to be essentially the solution. And then we're going to now formalize that into a probability distribution over the circle. So how are we going to do that? That's going to arrive at the von Mises distribution. So let's get started with that. Okay, so here we are. So let's get reading. So we've just discussed the periodic variables. Such quantities can conveniently be represented using an angular polar coordinate. 0 is less than theta, less than 2 pi. So almost everything in this chapter is going to be in radians, except for this example here. Okay, and this is actually a really interesting example. So we'll kind of work it out in detail together. And I think he's actually got a small mistake in a part of it. So we'll kind of see where that comes from. But his main point remains. Okay, so it says we might be tempted to treat periodic variables by choosing some direction as the origin, and then applying a conventional distribution such as the Gaussian. So for example, if you're working with angular data, you might think, okay, well, a particular direction is 0, and I'm going to measure everything relative to that. If you're working like 24-hour data, maybe midnight is going to be your 0 point, and you'll measure time relative to that. But in some sense, that kind of doesn't necessarily acknowledge the fact that 11:59 p.m. is just as close, is very close to 11:59, which is kind of the maximum value you can get, is very close to 1 minute after midnight. And so it's important to kind of use data that acknowledge that periodicity. And we're going to see in this example what happens when you don't. Okay, so yeah, so let's say we just do the naive thing, and we're going to choose some direction as the origin. So remember, we have polar data, so all we have are directions, and we're going to choose one of the directions as the origin. So we're going to choose one direction as the origin, and then applying a conventional distribution such as the Gaussian, because it seems kind of reasonable as a naive approach. But you immediately run into problems. So such an approach, however, would give results that were strongly dependent on the arbitrary choice of origin, right? This is kind of circular data. It shouldn't really matter. You don't want your data to depend on how you pick the origin, but here it does. So okay, so let's suppose, for instance, that we have two observations at theta 1 equals 1 degrees and theta 2 is 359 degrees. And we model them using a standard univariate Gaussian distribution. Okay, so now if we choose the origin at 0 degrees, then the sample mean of this data set will be 180 degrees with standard deviation 179. Okay, and that's already kind of weird, right? Because you're like, this is 1 degree, this is 359 degrees, so they're very close to each other, but your mean is 180 degrees, so it's like way out on the other side, and you have a huge standard deviation. Whereas if we chose the origin at 180 degrees, then the mean will be 0, okay, which is, that seems a bit more right, so that's the correct mean. But the standard deviation will still be, it's not actually 1 degree, it's 179 degrees. Whereas, these data are actually very close to each other, so why do you have such a high variance or high standard deviation? So let's just work through that example ourselves, just so you can see where this comes from, and it really drives home the point. So let's go over here. We're going to erase all this stuff. Let's just erase all of that. Okay. Good. Okay, so we've got data points. So let's say we've got, I'll call it our data is equal to, we've got 1 degree and we've got 359 degrees. Okay, and so in our first case, origin is going to equal to 0 degrees. Okay, so now then our theta 1 is going to be 1 degrees minus 0 degrees. Theta 2 is going to be 359 minus 0 degrees. Right, so just obviously they don't change. And now we want to compute the mean and the variance. So let's call it mean is just going to be 1 degrees plus 359 degrees over 2, which is 360 degrees over 2, which is 180 degrees, right? So that's where that comes from. And now let's just compute the variance. So the variance is going to be what? It's going to be the sum of the average of the deviation of the data points from their mean. So that's going to be 1/2 times, what do we have? We got 1 degrees minus 180 degrees squared plus 359 degrees minus 180 degrees squared, right? And the 1/2 is we have 2 data points. Well, what is this? This is 179 negative, once you square, the negative disappears. And then you got another 179 squared, right? And so there's 2 of them. So then this the variance is going to be 179 squared. So therefore, the standard deviation is 179 degrees. Okay, and this is really weird because if you actually just plot your data, let's say this is 0. Well, there is your 1 degree, say, and this is your 359 degrees, right? So you kind of want your average to be at 0 degrees, right? Like your average should be right here. And there shouldn't be such a big standard deviation. It looks like intuitively there isn't much variation. Right? That's very, very little standard deviation. And yet our procedure here is saying, well, our mean is 180 with a standard deviation of 179. So it's 180 with like a huge standard deviation. So clearly, that's not the case. That just gives the wrong answer. Okay, but maybe, let's try something else. So the next thing he's going to try is, let's try. So what does he do? He's going to try a different origin, right? If you choose the origin at 180 degrees, okay, so let's do that. So origin equals 180 degrees. Then theta 1 is going to be 1 degree minus 180 degrees, which is going to be minus 179 degrees. Theta 2 is 359 minus 180 degrees, which is 179 degrees. Therefore, the mean in this case is going to be 0. So that seems fine, which is kind of what we want. But what's the variance going to be? So the variance is just going to be minus 179 squared plus 179 squared over 2, which is again 179 degrees squared. So we got the same variance as before. So again, it's saying, okay, this time we fixed the mean, but the variance is still enormous, right? And again, so these problems we're getting is because we're just giving these numbers. And so 1 degree and 359 degrees, they're quite large numbers, and that we're not acknowledging the fact these are actually degrees on a circle. And so we're we're getting these like origin dependent situations. So how are we going to address that? Well, let's get to that. So the main approach, the main idea is to actually place our data points on a structure, on kind of a domain that has the periodicity that we need, which is the circle. So let's have a look. So let's consider the problem of evaluating the mean of a set of observations of a periodic variable. From now on, we shall assume that theta is measured in radians, okay? And we have already seen that the simple average, it will be strongly coordinate dependent. So we just saw that, right? So based on the origin of our coordinate system, we got different values for the average. To find an invariant measure of the mean, so we want something that kind of is invariant to how we choose the coordinates. Note that the observations can be viewed as points on the unit circle. So that's kind of this is the main, the main insight, and can therefore be described instead by two-dimensional unit vectors where the norm of the values is 1. So it just means putting them on the unit circle. Okay, so let's do that. So that's going to be figure 2.17. So here's kind of the situation that we have, and I don't seem to have actually any dots, so let me put in some dots there. So here are our data points. And then, so then the idea then becomes you find your average by averaging these points as vectors. So each one of these is vectors, and you do kind of the vector sum of them, which is what is being done here. So what we do is, instead we kind of find those points, and we compute this average here, and then we find the corresponding angle of this average. So you've averaged the points; it'll tend to be inside the unit circle, and you compute this angle. Now clearly this definition will ensure the location of the mean is independent of the origin of the angular coordinate. So I think what he means by that is that if we shifted our coordinate, axes, so that let's say, instead we, I don't know, let's say we move things, let's draw a new coordinate axis over here, and maybe it was, something like that. So now, our angle was like a little bit larger. Well, all of the angles would shift, and the location of that mean relative to those points wouldn't change. The actual value might change, but because that value is going to be relative to your new axis. But if you know what that angle is, then you will find that actually the location of that mean relative to the other points doesn't change. And one example of that could be, let's just apply it to, the case that we just had, right? So here were our 2 points. This was, this was the one that we call it 1 degree, 359 degrees. And now we're going to, average them. And so the average is going to be here. So the average is going to be what we're going to call in this current coordinate system, will be the 0 degrees. But now if we shift everything, so now let's say we shift everything. So now let's say our new coordinate system is like here. Well, this 1 degree thing, maybe this is actually going to become, I don't know, like 70 degrees, and this is going to be I don't know, whatever it is. So that's going to be 68 degrees, I suppose, because but this mean will still be relative to those guys because it's just going to be the average of those points, and this will actually do the right thing and will end up being in 69 degrees. So the number will change, but the relative position of that respects the fact these are periodic angular variables, and so it kind of changes with the shift in the with the coordinate system in the way that you want. Okay, so now note that x bar will typically be inside the unit circle. So now we're going to say, well, okay, so how would we figure out, let's figure out what this mean looks like. So the Cartesian coordinates of the observation are given by xn is cosine theta n, sine theta n. So that's kind of giving the x and y values. And we can write the Cartesian coordinates of the sample mean, so that's going to be this guy, as r bar, so this r bar, cosine theta bar, and r bar sine theta bar, okay? Now substituting 2.167 and equating the x1 and x2 components then gives so and so. Okay, so essentially what he's just done here is, you can look at this as this is going to equal to 1 over n. If we do it coordinate wise, it's going to be some cosine theta n, some sine theta n. And now we've said that kind of this thing is going to be r bar cosine theta bar, the x coordinate of the average. And then this thing with the minus 1 over n is r bar sine theta. So we just equate those. And that's what we have here. Okay, so that's kind of how we solve for this theta bar. So what we do is now we just say, well, let's take the ratio that will get rid of r bar, and we'll just leave. So let's just put 1. So we go r bar sine theta divided by r bar cosine theta, is going to equal to, so tan theta. Right? If you just take those ratios, because this thing is going to get canceled out. Therefore, theta bar is going to be tan minus 1 of sine theta. Sine theta over cosine theta, and so, and if we take this actual ratio, we'll see that the 1 over n's cancel out, and you just get the sums of the sines and the sums of the cosines. So that's all we're doing here. We're just taking the ratio of these two things. That's giving us this term, and that ratio is tan of theta theta bar. So we simply just take the inverse tan of it to give us theta bar itself. Okay, so it's another way of thinking about it is, we're just essentially just finding the average x coordinate, finding the average y coordinate, taking the ratio of rise over run, this over this to give you tan theta bar, and then you're just inverting that. So that's how you end up with this formula. Okay, so that was just for the mean. So we haven't really put any probabilities or anything on this. And so that's kind of what we're going to do now. So it says, shortly we will see how this result arises naturally as the maximum likelihood estimator for an appropriately defined distribution over a periodic variable. Okay, so right now we've kind of done things in kind of an intuitive way. We're now going to think about how to put probability distributions on the circle, and then we'll see that this quantity will just kind of emerge as a maximum likelihood estimate related to that. Okay, so now I just want to say, so the way he's going to do it, there are a few ways of doing this thing, and I'm just going to kind of give you an outline of the way he's going to do it. So the idea is going to be to consider a two-dimensional distribution, a normal two-dimensional Gaussian. That's this guy, and then relate it somehow to the unit circle. And the way we're going to do it is we're going to condition on the data points being on the unit circle. So we're going to say we're given this kind of two-dimensional distribution, and now we're going to say, well, condition on those points, condition on us being on the unit circle. What is the probability distribution we get on the points of the unit circle? And so the way that you would do this normally, I think he kind of skipped some of the steps. So I thought it might be useful to actually kind of point out what he's doing. So let me just zoom in a bit so we have a little bit of space. Okay, so the first thing he's going to do is, so we've got our probability and now we're going to switch to, implicitly, we're going to switch to polar coordinates. So we're going to write this as, this is P x r theta, y r theta. And now you know that you need, because of that determinant of the change of variables term, there will be an r dr d theta. Okay, so this is going to be, this term here. Let's just call this q of r theta. So that's going to be our density, our corresponding density for that two-dimensional distribution. We haven't done anything. We've just changed variables. Right. So we're going to call that q. And then what he's going to do is going to say, well, so now we're going to condition on being on the unit circle. So condition on unit circle. So now we're going to get a distribution where let's call it P of theta, which is going to be Q of theta conditioned on r equals 1. Okay, so we've got this two-dimensional, it's a polar, it's this blue thing here, but now expressed instead of in x and y, expressed in terms of r and theta. So and it's defined everywhere. And now we're going to condition, but to get it, we care about just this aspect of it. So what we're going to do is we're going to just condition. We're going to say, well, give me a distribution on theta, and the way you're going to give me that distribution is by just conditioning what you have here on your data points being at r equals 1. And that's what this is. Okay? The way he's going to do that is he's just going to say, well, this is the same as q of theta. So this is a joint distribution divided by the normalizing factor. Or you can just say, well, it's just going to be proportional to, so this is going to be the unnormalized version. And this will be a bit easier for us to work with because essentially we'll get this equation and then we'll just plug in r equals 1 and then just normalize. Okay, so because we need, p theta needs to be normalized, of course. So we just take this joint distribution, which won't be normalized. It'll integrate to something that almost certainly won't be 1, and then you'll just normalize it. So that's kind of what's going to be happening here. So I just want to kind of give you a sense of kind of the big picture, because then at the end of the chapter he talks about another method which uses kind of the same framework but takes a different approach. So we'll see where that comes in later. So here we're just going to condition on being on the unit circle, and the thing we're going to be after is this. Okay, so hopefully that was helpful. Now let's see what he has to say. Okay, so we now consider a periodic generalization of the Gaussian. And notice he says aperiodic because there's another one which I'm going to talk about in the next video, which is called a wrapped Gaussian, which in some ways to me is much more natural, but it turns out that it's a bit harder to work with. So, and that's where you just wrap the Gaussian around the unit circle. But it has this kind of some nice properties that I want to share with you. But yeah, for the most part, as far as I've ever seen circular data and circular distributions, the von Mises distribution that we're going to talk about here, that's the real star of the show because it has various nice properties. Okay, here we shall limit our attention to univariate distributions. So we're just talking about a single angle. And if you care about other ones, you can look at this book. Okay, by convention, we will consider distributions p of theta that have period 2 pi. Okay, any probability density theta, p theta, defined over theta must not only be non-negative and integrate to 1, but it must also be periodic, right? So these are kind of the basic things you need. Notice that we're integrating over 0 to 2 pi. For example, the Gaussian, we integrate over the entire real line, but here we're just integrating over 0 to 2 pi. And this is the key periodicity condition, that the probability of theta plus 2 pi is the same as probability of theta. And then from that, it follows that, if you do integer multiples, then of course it will be the same as well. Okay, so how are we going to do this? So he's going to do this approach that we talked about. So he's going to start with this two-dimensional distribution and then condition it on r being equal to 1. So we can easily obtain a Gaussian-like distribution that satisfies these three properties as follows. So consider a Gaussian distribution over two variables, x equals x1, x2, so that's going to be this guy, having mean mu1, mu2, and a covariance matrix which is just sigma squared. So that's why it's circular. The variance is the same in all directions. Write the 2 by 2 identity matrix. So that p of x1, x2, is this. Okay, and this is nothing scary about that. It's just x1 minus the mean in that coordinate, x2 minus the mean in that coordinate, and they both have the same variance, so it becomes like a very simple Gaussian distribution. The contours of constant p of x are shown on 2.18, which we saw, those blue curves. Now suppose we consider the value of this distribution along a circle of fixed radius. So now we're kind of building up to this. Okay, then by construction, this distribution will be periodic. That's because, it's just, you're literally moving back to the same point. So, as the theta moves, you come back to the same point, then you're going to get the same values again and again. So by construction, the distribution will be periodic, although it will not be normalized. That's kind of what we're talking about here, that what we end up getting is going to be this joint distribution of theta at r equals 1 is not normalized, so we'll just have to normalize it. But let's just figure out what that is. So we can determine the form of this distribution by transforming from Cartesian coordinates to polar coordinates, so that x1 is r cosine theta, x2 is r sine theta. So that's our guys there. We can also map the mean into polar coordinates by writing mu1 is r naught cosine theta naught, and mu2 is r naught sine theta naught. Okay, then the next thing we do is we literally just substitute these directly into that. Okay, so we're just going to plug them directly in. And now you're going to get, so what are you going to get for the first term? So it's r cosine theta, that's coming from this. R naught cosine theta squared, that's coming from that. And then r sine theta coming from this. R naught sine theta naught, that's coming from that. You're squaring them. You expand everything out. And then let's just do one part of the expansion so you see that, so you see what's going on. So for example, there's going to be an r squared cosine theta squared there, and an r squared sine theta squared. And then when you add these up together, you'll get r squared, right? But r squared, and then evaluated at r equals 1, that's just going to give you the 1. So you're just going to do all that and use the your trigonometric identities and the fact that we're evaluating at r equals 1. And you'll notice that we'll end up with a term that's 1 plus r naught squared minus 2r naught da 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 da. And then we use another trigonometric identity, the fact that this is cosine theta naught plus sine theta naught. Should actually be minus. No, it's actually plus. Yes, exactly as I wrote it. So that's where this simplification comes from. And so, and the key thing that he's done is, use that simplification to get this cosine term. And we've also discarded these other terms, right? Because all we care about is stuff that depends on theta. So like this whole thing, is absorbed in the constant term. When you put the exponential onto it, it'll just be exponential something that doesn't depend on theta. And when we normalize, all that stuff kind of disappears. So all we care about is what the dependence on theta is, and then we'll just normalize that. So we don't care about things that don't involve theta, and only this term does. So we end up getting 2r cosine theta naught, which is r naught, and when you divide it by the 2 sigma squared on the bottom, you end up getting, and let me erase all this stuff now, so it's a little bit clearer. You end up getting this plus a constant. So it's pretty cool. And don't forget that this is all happening inside the exponential. This is all happening inside this exponential here. All right. So that's how we've got. We made use, yes, these are important ones that you need to know about. And now we just define m. Notice it's kind of like an it's like a precision, right? Because the sigma squared is on the bottom. And it's kind of cool, right? Because it's like the variance, it's the length divided by the variance. So it's kind of like scaling that, the higher, the longer that length is, the higher your kind of precision is. Which is pretty cool. Okay. We've obtained our final expression for the distribution of p theta along the unit circle in the form. Where did this form come from? Well, so this bit is just what we just figured out. So this is directly coming from our expression here. We just called this m now. And then we're going to normalize it so that this whole thing d theta equals 1. Well, and to do that, well, that's where this, Bessel function thing comes from. So, so we just call it the von Mises distribution or the circular normal. Here the parameter theta naught corresponds to the mean of the distribution, while m, which is known as the concentration parameter, is analogous to the inverse variance, right? The variance is there. The normalization coefficient is expressed in terms of I naught m, which is the 0th order Bessel function, which you might know from physics. But notice that essentially all it is you would get this unnormalized distribution, and now you want to normalize it. You want to normalize it so that it integrates, to 1. So that this whole thing integrates to 1, basically. And so that's where it comes from. Even if you didn't know what it was called, you could just put it down. You could define it yourself in such a way that to make this whole thing integrate to 1. So don't be too scared by that. It's just a normalizing constant. For large m, the distribution becomes approximately Gaussian. Okay, and so the point of, and there's an exercise on this, but basically the reason why that happens is that, the cosine function, around, cosine of theta, let's say we had mean 0, is going to equal to, 1 plus, theta squared. I think it's going to be 1 minus theta squared. Plus So around its, around its peak, so around theta naught, it's going to look like a parabolic. And so you'll have, for very large m, if you have multiply that m in there, well, you'll get then, m cosine of theta, it's going to equal to m minus m sigma squared, and then maybe there'll be other terms, m squared, sigma to the 4th, whatever. But when these show up, maybe that should be a minus. M whatever sigma squared minus sigma to the 4th, all that stuff. When m gets very large, then all of these terms will you can kind of ignore them, and you end up with just this one as dominating. So this will contribute a constant. This will contribute kind of quadratic term, and if you ignore for very large m, you can kind of ignore some of the other ones, and you end up with a quadratic distribution around the mean, which is just like a Gaussian. So I think that's the intuition for it. You can kind of go and figure out the details of it in that exercise. Probably worth doing. Okay, so that's where we are. So the von Mises distribution is plotted in 2.19, and the function I naught m is plotted in 2.20. Okay, so let's have a look at what it actually looks like. Let me see if you guys, okay, so let's just look at it here. So in this particular setup, we have, this is going from, I guess, 0 to 2 pi. So we're just plotted in the normal kind of, we just pulled out 0 to 2 pi. And here is 1, so m here is large, and you can see that it is kind of like a Gaussian, right? Like, when you're far from the mean, this is pi over 4, I imagine. When you're far from the mean, it's kind of about 0, and then when you get close to it, it looks very much like a Gaussian. This one here isn't quite so peaky, so you start kind of getting some interesting like non-Gaussianity kind of going on. So maybe your normal Gaussian approximation wouldn't quite work so well, but the von Mises kind of takes care of that for you. And now we can look at the same data actually arranged in polar coordinates. So the way these work is that you look at the value from 0 to 2 pi, and then you just plot these amplitudes. And you can see for this one that's kind of very sharp, around pi over 4 has a large amplitude, but at let's say very orthogonal to that, its amplitude is very low. So you kind of get this kind of balloon shape. Whereas this guy over here seems like it's not quite so extreme. So it's got its peak at 3 pi over 4, but at let's say 90 degrees to that, it still has some. It's kind of a bit more uniform. So you can see the balloon is not quite so big. But that's kind of the way you would look at it, and that's kind of maybe to some extent reminiscent of those plots I showed you. So for example, here we were. Kind of looks like we have kind of quite a peaky distribution here, maybe, but these guys aren't quite quite so peaky. So cool. Okay, so now let me shrink this so can you guys see that? Yeah. Okay. Good. Okay, so let's continue. So that was kind of how we came up with the von Mises distribution. So we came up with it by conditioning our this kind of two-dimensional Gaussian on the unit circle. Good. Now let's consider the maximum likelihood estimated for theta naught and m. So now we have some data, and I want to estimate. We want to estimate that we assume comes from this von Mises distribution. Now we want to estimate theta naught and m. And so again, because we have independent data points, you end up getting. So what's our distribution looking like? It's this, and we have n independent thetas. So now we're going to maximize the log likelihood with respect to theta naught and m. So now when you compute the log likelihood, you're going to get these normalizing factors showing up n times. So this is minus n ln 2 pi, that's from that. Minus n ln I naught m, that's from that. The logarithm gets rid of the exponential, and now you have m, and then you have a sum, because you're multiplying these exponentials in the product. You get a sum of cosines, and now notice there's a theta n minus theta naught. So now we're going to do the usual thing, take derivatives with respect to theta naught, with respect to m, set those to 0, and see what we get. All right, so setting the derivative with respect to theta naught equal to 0 gives this thing. So let's just do that. So d theta naught is going to equal to, is going to be 0, 0 plus m sum n equals 1 to n. And now we're going to get a minus sine theta n minus theta but then there's also going to be a minus 1. So it's going to be, so we're going to get is equal to m sum sine theta n minus theta dot. And now we're going to set this to 0. So this goes to to 0. And now we use our trig inequalities. So, and now what is this sum? Well, this is going to equal to sum on n of sine theta n cosine theta naught minus cosine theta n sine theta naught. Right? So now we're going to get c cosine theta naught sum on n sine theta naught, let's just put that in brackets, is going to equal to sine theta naught cosine, right? And now we're going to rearrange. So we're going to divide. So then we'll end up getting, I think, has he already written it here? No, let's just do it. So it's going to be sine theta naught over cosine theta naught is going to equal to the sum on sine theta n over sum on cosine theta n. And what is this thing? Well, this is, tan theta naught. So that's going to, theta naught is going to be our maximum likelihood estimator of the mean. And so that's where you end up with this. So that's exactly this distribution. So theta naught ml is just the inverse tan of the sum of the sines of the angles over the sum of the cosine angles. So this is exactly what we had before when we just put heuristically put points on the unit circle. So which is we recognize as a result obtained earlier for the mean of the observations viewed in a two-dimensional Cartesian space. Okay, and so now we're going to go back and we're going to maximize 2.181 with respect to m, and making use of a property of this Bessel function that the derivative is equal to another Bessel function called I1. Okay, so let's try that again. So now we're going to erase all this stuff and do the same thing. So let's try it again. So, but now we're going to go dm is going to equal, again, it's going to be 0 minus n. This time the Bessel function is going to contribute, so it's going to be 1 over times I naught plus the sum on cosine theta n minus theta dot. And this thing, so when you set this to 0, we get I1 is going to equal to sum 1 over n to the average value of, and this function he's going to define as a of m. So the function a of m, so here we go. So right, so a of m, where we've substituted for the maximum likelihood solution for theta naught ml. Yeah, so this, he's saying that this theta naught is actually the theta naught that we actually figured out because we're setting both of them to 0. Or we have substituted for the maximum likelihood solution for theta naught ml, recalling that we were performing a joint optimization over theta and m, and we have defined a of m this way. Now the function a of m is plotted in 2.20, so it looks like this thing. Okay. Making use of the trigonometric identities in 2.178, we can write 2.185 in the form. So we're just going to expand this out. Right, so this is going to equal to, I'm just wondering, I don't think he's actually quite, shouldn't this be plus? I think that should be plus. Because, yeah, I think that should be plus. I think he might have this wrong because the cosine, so I think that's the way it's supposed to look. This is just 1 over n times the sum on cosine theta n sine, cosine theta ml plus sine theta n sine theta naught ml. Okay, so essentially but the point of all of this is that you've actually already figured out what theta naught ml is, so you plug that in. You already have the average of these points, and then you're not going to get a closed form solution for this. So you just go and look at this plot and you figure out, okay, so where, what value of m corresponds to the empirical value that you need to compute. So essentially you'll get some number for this, and then you can solve for the m such that a of m gives you that number. Okay, so there's a plus sign here, but otherwise I think that looks right. The right-hand sign is easily evaluated, and the function a of m can be inverted numerically. So yeah, so that's it'll be a simple, no closed form solution there, but you can figure it out on the computer very easily. Okay, so for completeness, this is the final stretch. For completeness, we mentioned briefly some alternative techniques for the construction of periodic distributions. The simplest approach is to use a histogram of observations in which the angular coordinate is divided into fixed bins. And this has a virtue of simplicity and flexibility, but also suffers from some limitations, which we're going to talk about in section 2.5. So that again, is exactly what was being done here, where they just built a histogram of. I don't think there was any inference being done here. It was just like, let's just look at the distribution of the data. So that might be and I would actually recommend you doing that as the first step anyway, just looking at your data in this particular way. But we can do, if we want to do inference and do other things, we can use the von Mises distribution to do that. Okay. Another approach starts like the von Mises distribution from a Gaussian distribution over Euclidean space, but now marginalizes onto the unit circle rather than conditioning. Okay, so, and I looked up this reference, but I think essentially what he means is, remember that what we've done, the way we define our distribution was we said, well, P of theta is going to be equal to Q of theta. This was our two-dimensional Gaussian conditioned. So this was the two-dimensional Gaussian, but conditioned on R equals 1. So that's what we've already, that was approach 1. Another approach could be, and I think that's what he means, is you could say, well, P of theta, and let's put it's going to equal to marginalizing out R. So you can, and I think, so in this particular reference, what they do is they just take every single data point, those 2D data points, and they just divide them by their length, so they all end up on the unit circle. So I think that might be the other approach. Seems like kind of the most natural kind of partner to what we've already been doing. But anyway, this leads to a more complex form of the distribution and will now be discussed further. And finally, and this is what I'll talk about in the next video, which I think has some nice properties, maybe not practical properties, kind of mathematical properties perhaps. Any valid distribution over the real axis, such as Gaussian, can be turned into a periodic distribution by mapping successive intervals of width 2 pi onto the periodic variable 0 to 2 pi, which corresponds to wrapping the real axis around the unit circle. Again, the resulting distribution is more complex to handle than the von Mises distribution. So that's why we're going to be working with the von Mises with the circular data. Yeah, and then finally, so one limitation of the von Mises distribution is just like the Gaussian, it's unimodal. But by forming mixtures of von Mises distributions, and we're going to talk about that literally, well, at least mixtures of Gaussians anyway in the next section, we obtain a flexible framework for modeling periodic variables. And here are some kind of examples of that. Okay, so I think that was a nice introduction to circular variables, which do come up, so they're really worth knowing about, having some familiarity with. And we just saw how the key idea was taking the points that you have and not thinking about them as angles, but as points on a domain like the unit circle that has the periodicity that you need, and then deriving the distribution on that by essentially conditioning a 2D Gaussian. And that's kind of honestly, I don't think that's the way I would have thought of it. The wrapped distribution we're going to talk about next time is I think a bit more natural, but it turns out that this is actually a bit harder to work with. But nevertheless, the von Mises is, condition that 2D Gaussian, condition a 2D Gaussian on the unit circle, and that's how you get it. So hopefully you found that useful. Please let me know if you did or if you didn't, and I will see you in the next video continuing on this theme of periodic variables. So hope to see you then. Bye.